Now we are discussing about the functional block diagram of operational amplifier. In the last class we have discussed about differential amplifier. This differential amplifier is capable of amplifying the difference mode signal, but it rejects the common mode signal. But in practical applications there may be possibility of even amplifying this common mode signal also. That's why we are defining a term called common mode rejection ratio, CMRR. This CMRR is the ratio of the differential mode gain and common mode voltage gain. We expect the common mode voltage gain should be 0 and the differential mode voltage gain should be high. That means we are expecting the CMRR should be infinite. CMRR is equal to differential mode voltage gain and common mode differential mode voltage gain and common mode voltage gain. We are expecting this to be 0 because differential amplifier we don't expect it should give the common mode signal. We expect this output should be 0. And when it becomes 0, the CMRR should be infinite. For an ideal op amp, we discussed in the later classes, the CMRR should be high. Operational amplifier. In the previous semester, we have learnt about the amplifier, but this is operational amplifier. This amplifier is capable of useful to us in real-time applications. It is an operational amplifier. We are trying to understand what are the drawbacks if we use a single-stage amplifier, and we are overcoming that by using a multi-stage amplifier. A multi-stage full-packed amplifier, this is called as an operational amplifier. The functional block diagram of this operational amplifier includes the 4 blocks. In the first stage, we are calling this as an input stage. We are using the differential amplifier. This differential amplifier is taking the 2 inputs, V1 and V2, as we discussed in the last class. One input is called as non-inverting input. This one, non-inverting input, is represented with plus, and one input is called as inverting input. This is represented with the negative. So here, when I am giving negative and positive, this is inverting input and this is non-inverting input. We have 2 inputs in the input stage. One is inverting input, second one is non-inverting input. We represent the inverting input with the negative sign and we represent the non-inverting input with the positive sign. So these 2 signals we are feeding to the input stage, which is a differential amplifier, and the output of this differential amplifier will give the voltage gain of the difference. So this difference will be amplified, V2 minus V1 will be amplified at this output. But still we are not satisfied with this output, still we want to improve the voltage gain. We are feeding this to next intermediate stage, which is again a differential amplifier. So when with this differential amplifier, still we are getting the high voltage gain. Second terminal we can make it as a grounded and we are making it as a differential amplifier, and still we are increasing its voltage gain. So voltage gain we have improved by using the 2 stages. But still this output voltage is not capable of, we are not capable of using it in real-time applications. For a simple speaker, I want to connect this voltage signal. We are not able to connect. What is the problem? This is very good voltage. It is having a very good voltage amplified signal. But the problem is power is very less. That's why in the last stage we use the power amplification. But before we are feeding to the power amplifier, we have to check that whether the DC level is correctly positioned or not. That DC level should be correctly positioned. For that we are using a level shifting stage, which is a emitter follower amplifier. The transistor is connected in common collector configuration. Input we give at the base terminal and the output we get at the emitter terminal. Whatever the input we are giving to the base terminal, that output will be appearing the same. Then what is the use of this stage? We are not changing the gain of the input signal. Already we got the sufficient gain. But this stage operation is to check the level. Only we are checking whether the level of the signal is properly positioned or not. If this is the output signal from the second stage, And if this signal is shifted to the positive level, then we are making sure that this level should be at the 0. This is what the level shifting is, nothing but if the signal is shifting to the positive, then we are bringing back again to the 0 reference level. If the signal is shifting to the negative, again we are bringing back to the 0 reference level, such that when we are giving the signal again to the power amplifier stage, the signal should be at the 0 reference level. So here we have done voltage amplification at the first stage, second stage further we amplified the signal, and the third stage we are checking whether the signal is properly positioned or not, whether the signal level is shifted to positive or negative peaks. We are checking whether it is shifted to the positive quadrant or to the negative quadrant. If there is no shift, then there is no problem. By chance, if the signal is shifted to the positive side or negative side, we are shifting back again to the 0 reference level. Then we are giving the signal to the power amplifier. Now this power amplifier is increasing the power of the signal. So here this is working even as a buffer amplifier also, because this buffer amplifier is having the high input impedance and low output impedance. This is having the high input impedance and the low output impedance. CB, when we are connecting in this common collector configuration, so here this output stage power amplifier, when we are feeding at the output, it will have the low output impedance. We expect for an ideal amplifier, input impedance should be high and the output impedance should be low. For this input stage, we are giving the very high input impedance, and the output stage we are getting the very low output impedance, because this is an operational amplifier. This should be worked in the real time. That's why input impedance we are making it as a high, and the output impedance should be very much low. In the last stage after the power amplification, we can feed the signal to your speaker or any real-time application. So in the operational amplifier, we are representing with this arrow symbol. This is the circuit symbol of the op-amp. This is how we represent the circuit symbol of the op-amp. This is inverting terminal and this is non-inverting terminal, plus VCC, and this is minus VEE. This is input V1 and V2 and output is V0. This is the circuit symbol of the operational amplifier. And this is, we already discussed, this is a multi-stage amplifier. Input impedance is high, output impedance is low. First stage we are using for the voltage amplification. In the second stage we are improving the voltage furthermore. And in the third stage we are checking whether the 0 reference voltage, whether the signal is below the original 0 reference level or above the 0 reference level. We are checking. If it is above the reference level, we are bringing back to 0 reference level. If it is below the 0 reference level, again we are bringing back to the 0 reference level, and then we are feeding the signal to the power amplifier. Now this power amplifier improves the power of the signal. This signal can be fed in the real time for our applications. That's why this is called as operational amplifier.